my notes up. Right, so there are a couple of terms I don't think we've covered. I'm pretty sure we haven't. From chapter 6, I'm just going to tell you what they are, maybe give an example of it happening. And then we'll be finished chapter 6 and we'll start intro to probability, where you get to see numbers again. Well, the experimenter effect. If you're conducting an experiment, right, so it's not observational, but it's an experiment, and you don't have enough controls on it. So you don't have, for instance, a single blind where the person who's receiving the treatment doesn't know, or double blind, a third party, a doctor, whoever it is who's recording what the conclusions are, whether the person got healthier or whatever. If it's just you collecting the data, there's an effect called the experimenter effect. If you can you imagine you deeply believe that something is true and that you're observing something and you're measuring something. And it's not that you're cheating, it's not that you're deliberately changing the data, but can you see how that can cloud how you interpret what you're saying? Especially in those situations where there's a judgment call to be made, like how angry someone looks, right? In a psychological thing. We call that the experimenter effect. That's an example of it, at least, where you've got your data is biased because there aren't any controls. So the person who's an example of that could be from the other effect. Suppose I'm interested in, let's see, whether or not a drug that you take is going to help you with a psychological problem. Let's say your psychological problem is that you're depressed and you have this new pharmaceutical, and you think this is the greatest thing since sliced bread. And so you're going to get 500 or 50, whatever the number is, volunteers who have this problem, and you give them the treatment. So they come into your office and you give them the pill and they say, what's this for? And you say, this is a new drug that I've created. It's going to be great for you. It'll reduce your depressions. Can you see that because the guy knows that he's getting the right, you know, he's getting the drug, and he has a tendency to want to please the doctor. And if you throw in placebo effect, won't that very often affect the conclusions about how effective your depression drug is, right? And so we don't really want that system. Now, the next effect is called the Hawthorne effect. And they've got actually a good example in the homework, so I'll just use it. They discovered that this group of people went to a factory, and you know the little clipboards with stopwatches, because they were timing how quickly people assembled radios, whatever it was, right? So it's a production line, and they come around with a little clipboard, and they noticed that when the lights were turned up, so it was brighter in the factory, people were more efficient, right? They produced them quicker. And they found that when they turned the lights down, they were more efficient. And they found when they kept the lights the way they were more efficient. They were more efficient than the rate at which they were producing it before the scientists came in. And what that is that, you know, that people change their behavior when they know someone's watching them. And so in a factory, if a guy comes around with a stopwatch and a clipboard, can you imagine why that might have the effect to make them work quicker? And so you have to be really careful that the Hawthorne effect doesn't kick in. In other words, you shouldn't be blatantly obvious what you're doing. Example of Hawthorne. Can you imagine someone's going about watching people drop litter, and every time they drop litter, they go on their clipboard and put a little check mark? Do you think that might reduce the amount of litter that's being dropped once people see somebody's watching them as they drop litter? You see how you influence behavior. That would be another example of the Hawthorne effect. Does that kind of make sense? That can affect your data. The next one is that there is a difference between what's called an interacting variable and a confounding variable. An interacting variable is a second variable that works with the first one, and it's the two of them that together interacting with each other that are causing the result. So I think they have one, but I'll pick one of my own. Let's suppose you looked at, I'll try to think of one. Yeah. You take a headache pill, right? And you see if it reduces your headache. And take the pill, whatever it is, how many said they got their headache reduced. And then you found out that if you just give people some relaxation techniques, right? Sit quietly, shut your eye, take a deep breath, think of something pleasant like the seaside, that you can very often reduce their headache as well. And if you put both of those together, you will reduce the headache even more. So you can see one of them might reduce, you know, it's a 60% effective, and the other one is like 30% effective. But when you stick them together, it's like 95% effective. So if two things are equally affecting the result, or at least affecting the result, but together they do an even better job than they do on their own, then these would be interacting variables. Cancer treatment uses this feature a lot. Do you know if you get treated for cancer, it's not that uncommon that you don't just get treated with one treatment, but a combination of treatments, because they found that the interaction of, say, chemotherapy along with radiation treatment, well, it's chemotherapy along with pills, along with some other things. In some places, they even introduce like life coaches, because if you can make someone positive and think, I'm going to beat this, it actually does have an effect on the success rate, right? You know, if you just give up and die, you're more likely to give up and die, right? But if you can be, you know, given some training to make you more positive, that is another interacting variable. And you can have situations where there are 3, 4, 5 interacting variables. It works in the negative as well. You know, you could have 2 pills. Pill A is for blood pressure and pill B is for headaches. Can't they interact separately? Aren't they quite safe? But can you imagine sometimes when you put them together and they interact in a very negative way? So that would be another example. A confounding variable is more like the variable that you're looking at isn't the real reason. There's another variable behind that. So you remember the number of TVs and how long you live, right? The confounding variable was actually wealth. TV had nothing to do with it, right? Really. So that's the kind of difference. Interacting variables do have an effect, and there's more than one of them. In a confounding situation, the variable that you're using isn't the real cause of whatever it is you're measuring. There's some other variable, the confounding, but typically a singular. Raven, do you have a question?
No, I'm good. Sorry.
No, it's okay. They're a little yellow thing, and sometimes that means someone's trying to talk. Are we cool with those things? So what you're going to get in the homework are stories, and it says what one of these effects are you saying? Right. Excuse me. Where is it, Celeste? It's in here. Okay, that was just my wife interrupting me. If you're wondering what that was, she needed something. Okay, let's get move to the next section. That's it. Chapter 7, Intro to Probability. Probability is something that is part of everyday life, even if you're not aware that you're doing it. everyday conversations or just thinking about what's happening around you, and we'll use the language of probability. You might say something like, there's a good chance it's going to rain today, or the chance that that couple will ever get married is nil, right? Or I'm feeling lucky today. I think I might go to the casino and win a lot. So when people talk about things like that, what they're really doing is expressing what's called probabilities. And probabilities is essentially the likelihood, right, the chance of a particular thing, we call it an event, happening. So probabilities is a number. It's always a number between 0 to 1, or if you do it as percentages, from 0% to 100%. I'll be continuing this sentence in a minute, but if I went and said to you that there's a 90% chance of it raining today, would you agree that's going to happen a lot more often if I said that the chance is 10%, right? So we have a percentage. In fact, I think the weather people do that, don't they? When they do forecasts, they say there's a 30% chance of snow or a 50% chance of being rain or whatever. So that's what they're saying. Now, it doesn't mean that you only get 50% of your rain. It means that sometimes it rains and sometimes it doesn't. And 50% is roughly a half, isn't it? It is a half. So half the time it does rain today, and then, the next time they say it, it doesn't rain, right? But on balance, it's 50%. So the probability is a number between 0 and 1 that tells you how likely an event, right, something, is likely to happen. What we're going to do is actually, for the most part, we're going to find ways to calculate these probabilities. Now, the probability of any event A happening is really made up of a fraction. And the top one is the number of ways A could happen. And that's divided by the total number of possible events. So pretty much every probability can be calculated using this very generic formula. So let's give you an example of that. Now, suppose you take a dice. It's got 6 numbers on it, right? 1 to 6. Sure, you've all played games where you roll the dice. If I said to you, what's the probability that you roll a dice and you get the number 3? Then you would say, well, how many ways could you get a 3 on the dice? Well, would you agree on a normal dice, there's only one number 3, so there's only one way of that happening. Now, what's the total number of possible events? Well, when you roll a dice, there are 6 numbers that could happen. So the probability that you roll a dice and you get the number 3 is 1/6. And probabilities are written in 3 different ways. You can write them as fractions, which in this case is a pretty good idea. You can write it as a decimal, in which case you're probably going to have to round it off. Or you can write it as a percentage. So I could say the probability that I get a 3 is 16.7% of the time. Probability I get a 3 is 1/6 of the time. And the decimal in the middle would be the probability that I get a 3 is 0.167, right, of the time. Now, if I say to you, what's the probability that I throw a dice and I get an even number? Well, on a dice, there are 3 even numbers, right? A 2, a 4, and a 6. And on the bottom, there's still 6 numbers. But in this case, you can simplify the fraction. So if you're given the answer in fractional form, right? So if they ask you to find a probability and it's to be a fraction, you're expected to simplify it. So that would be a half. If they wanted it as a decimal, wouldn't you divide 1 by 2 and get 0.5? And if they want the answer, less likely, but if they want it as a percentage, you can get 50%. So if I was a gambling person and I was betting money and I win when it's an even number, won't I win 50% of the time? Right? Or half the time if you want to call it a fraction. Any questions so far? Now, because of the definition that I've given, not just me, but in general, how we give probabilities, probabilities only have values from 0 to 1, right? Or 0% to 100%. So let's look at the extremes first. What could you tell me about an event which has a probability of 0? So the probability it happens is 0. What kind of event would that be?
Something that's impossible, something that could never happen.
Correct. So examples of that, the probability that I will become the president of America. And since I'm not an American citizen, that is guaranteed. And the fact that I don't like politicians and will never go into politics is probably certain. The probability that every politician in America will tell the truth one day, that would be 0 in my opinion. So at the other extreme, what about things that have a probability of 1?
Sun setting this evening?
Yeah, well, that's probably 0.999999, but couldn't our sun go supernova and we don't get a setting sun? But darn close to being guaranteed, right? 100%. How about we're all going to die one day, which again is probably the same kind of thing. Oh, couldn't you roll a dice and get a number 1, 2, 3, 4, 5, or 6? Wouldn't that be guaranteed because you're going to get one of them? So these things.
I guess it depends on the dice.
Yeah, I guess if you had a weird dice, it could change the rules. This will. I don't know why I said always. This will. There we go. That's what I wanted. This will always happen, right? So if you have the thing and it's a probability of 1, it's going to happen. Now, right in the middle, we have 0.5, which is 50%. We even have terms in the English language that are representing that probability. Have you ever heard that people say, yeah, it's a 50-50 chance he's going to, make it or graduate or something? It's as likely to happen as not would be another phrase that would fall into the 50% category. Yeah. So we kind of have particular phrases that are actually connected to it. So that there is basically a situation where half the time it happens, right? And then the other half the time, it doesn't. So I'm going to give you a list of possible probabilities, and you're going to say yes or no to could this be a probability? So I've got a 0.75, 302%, 14/11, 1/3, -1.2, 25%. Okay, here are some numbers, percentages, decimals, and fractions. Some of these could be probabilities, and others will never be probabilities, right? Give me one that's not a probability, could never be one.
I don't think 14/11 could be one.
Would you agree that there's a problem with 14/11? And the problem is it's too big, right? Can't be bigger than one. So when you're looking at fractions, if the numerator is bigger than the bottom number, doesn't that mean it's impossible? So if you ever do a calculation and that's the final answer to the probability of this story, will you immediately say, no, it's not, I've screwed up, let me figure out what I did wrong? Okay, there's another one that's not possible in this list.
302%.
Isn't that just too big again? What's that phrase that they do when they're in sports, you know, coaches? My players are going to give 150% or 200%. Does that not annoy you when the most you can ever give is 100%? That means everything, right? You can't do more. I know why they use it, so kind of turn a phrase. Right, there's one more in here that's got a problem.
Is it -1.2?
Okay, what's the problem with that one? Yes, by the way, you're right.
It's too small.
Yeah, in fact, anything that's negative, isn't it going to be too small? So probabilities have to be in the range 0 to 1 or 0 to 100%, right? They just have to be because of the way they're defined, right? So let's see if there is a way in which we can at least estimate the probability of something happening. So suppose I'm interested in the probability that I pick a person and they have red hair. Now, what we're going to do here has got a very fancy name. It's not fancy in the concept, but it has a fancy name. It's called empirical probabilities. And the other one are called theoretical probabilities. Right, so back to, I want to know what's the probability that I randomly just pick someone in the street and that they happen to have red hair. And we can define what red hair means. And the way I came up with this number is I randomly found or looked at 1,000 people. Right, so I, do a nice simple random sample. I collect all the good data, and it came out that the percentage of people who had red hair happened to be 35 of them. So the probability is 35 out of 1,000 people, which as a decimal, check I get my decimal point in the right place, 35 divided by 1,000 is 0.035. And to me, I like percentages. I don't know why, but they just seem easier. Would you agree that a 3.5% just is easier to get your head around what it looks like? Whereas decimals, it's hard to tell how big they are, I guess. So does that mean that the probability of getting a red hair is 3.5%, and that's guaranteed to be correct? Or is it more likely like an estimate? In this story, is this a guaranteed, if I go out now and go to Kansas and I randomly look at somebody, there's a 3.5% chance that person I look at's got red hair?
No.
No. So what we're looking at in empirical probabilities, isn't it, that we're looking at an estimate of what we believe the right answer is, right? Now, I could, I guess, do a census, couldn't I, find everybody in America and find out what colour their hair was, right? In which case, it would turn into a more precise one. But very often, empirical probabilities are the way that we have to calculate things. Weather forecasting is very often based on empirical probabilities. Haven't they collected a lot of weather from the last 150 years, whatever it is, right? A lot of data on weather. And from that data, they can make predictions about what the weather today is going to be like, because they have a bit of theory about, you know, what weather systems do, but don't they also, you would expect them to say, well, the last 100 times the weather was like the way it is today, 55 of those times it rained that day. Can you see that's how you could come up with a 55% chance of rain? You just find enough days similar to your one. Now that is our empirical probability. An example of a theoretical probability would be something like this. I want to know the probability that I pick a card from a deck of 52, right? There's no jokers in it, and that I get a red card. Now, in this case, I can actually do a kind of sensible theory of. In a deck of cards, there are 52 cards I could pick. Wouldn't that be the bottom thing, the total number of events? Now, hopefully some of you know what cards look like. They're hearts, clubs, diamonds, spades, right? And 13 of them are hearts, which are red, and 13 of them are diamonds, who are also red. So when you add them up, you get 26. And you see in this case, depends how you want to write it. So in this second situation, I haven't actually even got a pack of cards, and I don't sit with that pack of cards and randomly say, okay, that was a red. Then I do it 5,000 times, right? And when I did it that 5,000 times, you know, exactly half of them would be red, because actually that's not what happens. This is the theoretical probability of picking a red card, agreed? 50% of the time it's red. Now, if you did an experiment and you decided to take a deck of cards, give them a shuffle and pick a card, and then say it was red or it was black, right? You record it. Put the card back in, shuffled it again, did it a second time, put it in, kept on doing it. If you found the what's called the relative frequency of the reds, you might do it 100 times. But couldn't you end up only getting 48 of those times being red? Now, you could do it another 100 times. And the relative frequency of getting a red, by the relative frequency, it's really this guy. I just don't want to call it probability. Couldn't it be 51 the second time? Now, does that contradict this? No. Isn't this a finite number? And this is, if you could do it infinitely number of times, it would average out at 50%. They have a lovely phrase if you want to impress people. So here, I'm going to put it down for you. And look it up online. It's not made up by me. I hope that's how you spell phenomena. The empirical phenomena of statistical regularity. So if someone talks to you today and they say, what were you doing in your statistics class? You just say, oh, we were looking into the empirical phenomena of statistical regularity. Now, does that not sound impressive? What on earth is it? Well, let's do the red card thing. The x-axis is the number, we call them trials, which is the number of times, you know, 100 times or 1,000 times I did it. And here is the relative frequency of picking a red card. And I'll put there in red, just so we can see it, 0.5. And so we do it 100 times, 200 times, 300 times, and so on. Maybe squeeze one more, 600 times. And when we did it 100 times, we got a little bit less than half. When we did it 200 times, it was a little bit more than a half. 300, it was like this. 400, it was like this. 500, it was like this. And 600, it was like this. What you tend to get is a little ziggy-zag pattern. Do you notice that as the number of trials get bigger, doesn't the relative frequency get much closer to being 0.5? So if I had the time and patience, couldn't I do this experiment 1 million times? Now, I won't get exactly 500,000, but wouldn't 490,000 actually be very close to being 50%? It would be 0.49. And this is what the empirical phenomena of statistical regularity says. It says if you are going to try and get empirical probabilities, the more times you do it, the closer it is to being the real answer, right? The theoretical answer. Kind of useful. So if you are thinking, hey, maybe I can use this to be good at gambling, with a few exceptions, some of which are cheating, probability doesn't tell you what's going to happen. It tells you the chance that it's going to happen. So here's a story for you. You're playing roulette, and we'll make it a simple story. You either bet red or black. You don't like green, so you never bet green. And in this story, it even has a name. Called the Monte Carlo fallacy. In this story, right, imagine you're there, physically there, and you're just watching the casino and the roulette table. And they've already done it 100 times. And 82 of them, 82 of those times it's been red. And you've got some money and you're about to gamble on red or black. And so you would be looking at that and you would say something, two versions of it. The first one is reds are hot tonight, right? Reds are the lucky color. I'm going to bet my house money, right? All my money from my mortgage money, I'm going to bet it in red because red are hot, they're happening a lot, I'm going to win. And then there's another group of people who says, wait a minute, it's roughly, we'll forget about the green, it's roughly 50-50. It's time now for black to turn, right? So I'm going to put my mortgage money on a black, because they're meant to even up, aren't they? We'll pretend there weren't any greens that happen, right? Can you see that, both ideas of what probability is telling you is wrong? Because in the next roll of that little ball around the table, roughly, isn't the probability that it's black is still 50%, and the probability that it's red is still 50%. Because in every spin of that roulette table, aren't the chances the same? Now, if you thought that there was some logic to this, let's pretend for a minute how that could happen. Wouldn't that little ball have to know how many times a red has happened and how many times a black has happened? Right? It'd have to have a memory. Do you think that little ball's got a memory? Do you think it knows what happened the last time? Not only would it have to have a memory, wouldn't it also have to have a motivation? Hey, my job is to be 50-50. I've done too many reds here. I'm going to try and jump over and get into a black one. I mean, isn't that kind of stupid if you think about it? Yet the number of people who think probabilities are telling you what's guaranteed to happen, look at probabilities that way. I'll give you a simpler example. I've thrown a coin in the air, well, not actually 100 times. I've only thrown it in the air 99 times. And 50 times it came up tails. And 49 times it came up heads. And they're about to throw one more throw, right? The last one. What do you think the chances that that last throw, right, the 100th throw, what do you think the chances are of it being a head?
Slightly lower than tails.
Do you think that's true?
Well, it's supposedly 50-50, but
You're falling for the Monte Carlo fallacy, Ian. Wouldn't the coin have to have a memory and know how many times it was heads and tails, and also know that its job was to even them out?
I suppose not.
No. So the probability that you get a head, isn't it still half the time? 50% of the time. Gamblers make this mistake, which is why Vegas is still there. If it was easy to beat the odds, wouldn't Vegas go bankrupt? Isn't the reason Vegas is there is because they have the odds on their side. They know the probability of every game that they play, right? No matter what game you look at, they know the chances that someone's going to win, and they know the chances that you're going to lose. All they need to do is make sure whatever game that's being played, that the chances of winning are lower than the chances of losing, right? In other words, they always make money in the long run. Now, the fact that Matt can go down there and win $1,000 at, Caesar's Palace doesn't change what I just said. Because if Mark wins $1,000, didn't Ian go down last week and lose $2,000? You see, so they only use someone else's money. So that's essentially how gambling works. So if you go to Vegas, which I love, don't go with the expectation that somehow you're going to win, although it's really nice if you do. Go with the expectation is that the excitement of gambling, and you're paying for it. And that way, well, I have to because I'm absolutely useless at gambling, but I like it. It's fun. Are we cool with this? Are you getting a concept of how our probabilities work then? Right. Let's calculate some probabilities then. And the ones we're going to do are theoretical ones right now, and then I'll do some empirical. I guess I should start with cards because I assume people know what cards are, but not everyone knows cards. So here's a kind of summary of cards. In no particular order, you've got diamonds. We always do the 52 card one, right? So there's never going to be jokers in any of our questions. So you have diamonds, clubs, hearts, and lastly, spades. Your diamonds look like that, and they're red. And spades, because I can't draw them, look like that. That looks like a heart, doesn't it? It's got a little thing up there. They're black. And clubs kind of look like that. And hearts look definitely much more like a heart, right? Now, put in what they are. Diamonds are red. Hearts are red. Clubs are black. And spades are black. Now we call these suits. So we say the red suit or the black suit. Now each suit has the same types of cards. There's an ace, there's a 2, there's a 3, there's a 4, there's a 5, there's a 6, there's a 7, there's an 8, there's a 9, there's a 10, there's a jack, there's a queen, there's a king. So if you're not aware of cards, that's what they have. Does anybody know the name, maybe more than one name, but the name you give to the jack, queen, and king.
Face cards.
They're called face cards. So you might get a homework question that says, what's the probability of getting a face card? Right, so now you know. Hopefully you know that guy. He's called an ace. Right, we're not going into the values of these cards, but if you wanted to do probabilities, in a lot of games like blackjack, these count as 10 points. And that one is strange because it can be 11 or 1, and the rest are the numerical value. So, but people who are into any kind of gambling game with cards have to be really good at probability if they want to be successful. Because what you're doing is you're playing against other people, right? And so you want to be able to make sensible judgment calls about what's the chance that I am likely to get the card I need to win, and then base your gambling on that. So in blackjack, you're trying to get 21. In poker, it's more complicated because there's lots of different hands, and some hands are better than others. If any of you, probably it's not a thing you watch much, but if you ever watched the TV program where they were showing you poker, a poker competition, and they tell you things like, even before the last card's turned over, don't they tell you things like, oh, this guy's got an 80% chance of winning, right? And the other guy's got 20%, right? If they're just down to 2 people. And you might think, well, where do they get those percentages on? They get them from probabilities, right? And the probability of getting a particular card and winning compared to someone else. So now that I've set this thing up, what's the probability that you get one card and it's a 5? Well, there are 52 cards in a deck. Don't you just need to know how many of them are 5s? And that's right. And then you would simplify. So let's just assume that these questions are all to be given as fractions, right? Now, if I went and said to you, what's the probability that you get a red 5? Agreed? 2? Now, what's the probability that you get a face card?
12.
12. Now, if you wanted to figure, well, there's more than one way to count it, but here's one way to count it. Aren't there 3 face cards in each suit? Right, there are 3 hearts, 3 clubs, 3 diamonds, 3 spades. So 4 lots of 3 get you 12. And so what would that be? That would 4 into that would give me 3 13s. Are you comfortable about how you could calculate probabilities for a deck of cards at least? Because won't the bottom number always be 52? Mark's got his own educational aids there, right? 52 goes in the bottom, and the top is whatever it is you're being asked to calculate. Okay. Do a dice, it's an even simpler example. Okay, what's the probability that you get an odd number? Well, there are 6 in a dice, and 3 of them are odd numbers. 0.5. Now, when it's a single dice, would you agree there's not really that many questions you can ask? You kind of run out of questions pretty quickly. So let's up the ante and talk about a thing called sample space. When the event that you are trying to find the probability of becomes a little bit more complicated, it's very useful if you can write down all the ways things can happen. And when you do all the events that could happen, right? If you write down all the events that could happen, we call that a sample space. What that allows you to do once you've written down a sample space is it allows you then to find other probabilities for more complicated events. So I'm going to do an example of that type of thing. You have got Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Right? There are 5 days of the week in which you could be born, right? I was born on a Sunday, right? Actually, I think I was born on a Wednesday. I'd have to look that up. I was kind of young at the time, so I can't quite remember. But I was told, I think I was born on a Wednesday. So suppose you had 2 friends. And you wanted to do probabilities like, what's the probability that both my friends were born on the same day of the week, right? So we're both born on a Monday, both born on a Tuesday, right? Whatever it is. What's the probability of that happening? So I'm going to calculate the probability that both friends born on the same day. Now, the sample space are all the possible things that could happen, right? Couldn't you be, one of your friends born on a Monday and the other was a Tuesday? Or the first one was a Tuesday and the other one was a Monday, right? All these events are possible. Now, because Tuesday and Thursday kind of start with a T and Saturday and Sunday also starts with an S, I'm just going to call these A, B, C, D, E, F, and G. It's just a code, right? So if I say G, it means Sunday, right? Now you want to set out the sample space. That is everything that could happen. You have to be really careful about this because there are lots of things that could happen. So I'm going to set it up in a table. And A, B, C, D. Oh, I have to keep going on it. D, E. There we go. Now, I'm not going to complete that table, but we can pretend I have. First thing to notice is how many different events are in this sample space. Basically, that's asking how many boxes are there.
Is it 49?
Correct. Isn't there 7 rows and 7 columns, right? 7 days for your first friend, 7 days for your second. Now that guy is going to be my bottom number. So the probability that both my friends are born on the same day is going to be out of 49 days. Agreed? Now, since I'm not going to fill all of this in, I'm only going to fill in fact, I'm only going to put little stars on them, little asterisks, of the ones where they're both born on the same day. Would you agree? Both on a Sunday, both on a Monday? Now, if you go and look at that, that adds up to, I believe, 7, doesn't it? And so the answer is 1/7. Does that seem okay? A bit bigger than you thought? Less than you thought? What does it look like to you? That's just a judgment call.
Bigger.
Now, you've probably got more than 2 friends, agreed? I would assume, right? Most of my friends are my family, actually, but whatever, right? You've got, so you could try that. Let's suppose you get the 3 closest friends you could get. Couldn't you do an example of this and just pick 2 of them and figure out if they're doing it? It's going to harm. So in this room, there are about 20, there are what, 16 of you. Okay, 2 of you in this room probably have 2 friends born on a Monday or a Tuesday, right, the same day.